Hi, this is Jack from TritiumSoft.com talking to you today about BulletCalc3. Let's get started. So last time we talked a little bit about the functions of the buttons in BulletCalc3. This time I wanted to talk to you about the equations that go behind the operation of BulletCalc3. So when we press this calculate button here, it's taking all 5 of these values: muzzle velocity, target distance, caliber, bullet mass, and drag coefficient, and tossing them into a standard equation which goes over and estimates energies and what the force of drag is on the bullet, all the way from the muzzle all the way to the target. And it also calculates, well, for that amount of time, how far is this bullet dropping? And so, and at what speed is it going to be falling at the time that it hits the target? And so where these equations come from is, if we go over here to our Safari, you can see I've opened some of these things here. So all of these ballistic calculators rely upon a mix of this drag equation here, which if you went to NASA, you can find this drag equation. And so what drag is you have this coefficient, which we have a coefficient in our equation that we can adjust, times the density. So the density is, we're using lead, and so the density of lead is a very specific number, and it's constant because we're normally not shooting anything but lead. If you were going to shoot something other than lead, well, you would have to adjust that. But everything in our equations is all lead based. So our density is fixed. And then we have the velocity squared divided by 2 times the reference area. And so that's what gives you the drag. And so one other thing about drag here is it's saying that it depends on the size and shape. So if we look at shape, what do they mean here? And so it is that there's some specific coefficients of drag for different shapes. And so, for instance, for sphere, it was saying 0.07 to 0.5. For a flat plate, 1.28. So it makes sense that there's more drag from a flat plate than there is from a ball. And then if you can see over here on the right, it says there's one for bullet, 0.295. And so if we went back into our program, what we can see here is, if I press change units, on change units, that information is right here under drag coefficient. So for a lot of publications, they'll say the coefficient of drag should be 0.1 to 0.3 for a rifle, and for a sphere 0.5. But the thing to remember about this is we're dealing with real world situations. And so what I mean by that is, if you're out at a range and doing sighting and running with measuring the velocity of your round. So for instance, I shoot a lot of muzzleloader, and muzzleloader, I can't just go to Wikipedia and say, how fast is this going? I have to measure these things, and they are very difficult to measure sometimes, because if you're running muzzleloader, if you're shooting muzzleloader, there's all sorts of things that are coming out of the barrel. You have unburned powder sometimes, or smoke. You have patches, you have wads, you have all sorts of things flying out of that barrel, not just a nice clean round like in a lot of modern firearms. And so measuring the velocities can be more difficult, and they can change based off of incomplete ignition, or you change the amount of powder, things like that. And so, or how dirty the rifle is. These things can make a difference. And so being that that's the case, what we can do is we can adjust this number. So one thing that's nice about BulletCalc3 is that I've put in controls so that if you pick a number that is ridiculously high, it will change it back. And so there's a maximum value here. And that maximum value is based off of NASA's shape table. And so while I can put in a I can put in a 1.5, I can't put in a 2.8. And so it helps minimize fat finger errors. The other thing about this equation here is if we go back in here, I also have other tables. So for instance, the way to use this program is if I look at this box of Winchester here, they have a ballistic table, 100, 200, 300, 400, 500 yards. And I can use this data to help me find what ballistic, what coefficient of drag I should use that better matches this data, because Winchester has provided it. Maybe it works in my situation, maybe it doesn't, but it's a good start. And what it means is if I can match these data with my equation very well, then what that means is I should be able to approximate other values, like maybe 150 yards or 1,000 yards possibly. It gives us a better understanding of the round that we're shooting. There's a lot of different situations, but there's a basic relationship as well. And that basic relationship is if you're comparing guns that shoot enormous rounds on battleships versus out of your rifle, when you have a real big, heavy round flying out at a certain speed, it's going to lose less energy per foot compared to its overall energy than a little bullet. And the reason is because it has, that it has a lot more energy to lose, and it has a streamlined shape. So, for instance, if you looked at shotgun pellets lose energy very quickly, in part because they're so small, and so that the drag is very high compared to the energy of the inherent projectile. And so, generally speaking, bigger, faster goes farther. Heavier, faster goes farther. So with that, we'll come back and talk a little bit about shock waves on the next video.